There's this saying in computer science that I think perfectly captures the essence of what we're going to explore today.
Oh, yeah.
Yeah, the saying goes like this: the fastest computation is the one you don't have to perform.
Right, right. That is a classic.
And I want you, the listener, to really think about that for a second, because we walk around with these incredibly powerful supercomputers in our pockets, right?
Oh, yeah, absolutely.
And we tend to imagine them furiously calculating, billions of complex mathematical operations every single second.
Which they can do, but
But what if I told you that a huge portion of what we consider computing is actually just an elaborate illusion?
yeah,
That your devices are often just remembering things rather than actually calculating them.
it is, it's really the ultimate work smarter, not harder approach to engineering.
Exactly. And that's the mission of today's deep dive. We are exploring this massive, highly detailed presentation on table lookup algorithms, from Cordic to EDA.
It's a fantastic source.
It really is. It outlines this entire compute once, lookup forever optimization strategy. And to help synthesize this really dense material, we've got our expert here.
Happy to be here.
Yeah.
And, to set the stage, we are really talking about table lookup or TOU algorithms.
Right.
And the fundamental idea is just beautifully simple. You're amortizing an expensive runtime computation over many, many fast memory accesses.
So doing the hard work up front.
Exactly. Instead of, doing the heavy math when the program is actually running,
Uh-huh.
you pre-calculate all the possible answers ahead of time. You store them in a massive list in memory, and then you just look up the answer when you need it.
Okay, let's unpack this, because before we dive into the dense algorithms from today's sources, which, by the way, cover everything from early computing to designing million-gate microchips, we really need to understand the speed-memory trade-off.
Yeah, that's the foundational concept.
Think about it like a busy restaurant kitchen. Imagine a customer orders this really complex chopped salad.
Okay, I'm with you.
If you compute that order at one time, the chef has to pull out the cutting board, wash the lettuce, chop the tomatoes, dice the onions, assemble it from scratch every single time.
Which takes serious time. You're holding up the whole line.
Exactly, that's runtime computation. But a table lookup approach, that's the prep shift.
Right, right.
You come in at 5 a.m., you chop hundreds of salads, you put them in the fridge. When the dinner rush hits, you aren't cooking. You are just opening the fridge and handing them a salad.
You traded physical space, like fridge space in the kitchen or in computing, memory for raw, unadulterated speed.
Yes.
The restaurant analogy perfectly captures the physical reality of a microchip, because you are quite literally trading silicon real estate for time.
Which is always the big trade-off in hardware.
Exactly. And what the source material points out is that this speed-memory trade-off generally falls into four major patterns in computing.
Let's hear them.
The first is function approximation. So if you need to calculate a complex sine wave, the actual mathematical algorithm to draw that curve is painfully slow to converge.
Like Taylor series stuff.
Yeah, exactly. It's iterative and slow. But if you use a sine lookup table or a gamma table, you bypass all that slow math and just pull from a list of pre-calculated points.
It's like an animation flipbook instead of rendering a 3D movie on the fly.
That is a perfect way to describe it. Then the second pattern is finite field arithmetic.
Which sounds pretty intimidating.
It does, but it essentially means taking brutal mathematical operations like massive polynomial division and just swapping them out for a simple addition and a cheat sheet.
Okay, yeah. And we are going to see a crazy example of that later when we talk about cryptography.
We definitely will.
Yeah.
Now, the third pattern is state machine acceleration.
Right.
If a system has a complex set of rules for what it should do next, based on what just happened, calculating that logic dynamically takes time.
So a table just...
The table just instantly points you to the next state in a single cycle. Boom, done. And finally, the fourth one is memoization, which is essentially caching. If your program encounters a complex puzzle it has already solved, it reuses that subproblem. It just looks up the saved answer instead of solving it from scratch.
Which brings us from the abstract concept to the grandfather of all table-driven algorithms. The one that basically built the digital world, Cordic.
Oh, Cordic is amazing.
It stands for Coordinate Rotation Digital Computer. But I have to admit, looking at the source material, I was a little skeptical of the premise here.
How so?
Well, the claim is that Cordic calculates complex trigonometry sines, cosines, tangents without using any multipliers in the hardware.
Right, zero multipliers.
But how do you rotate a coordinate on a graph without multiplying anything. I mean, my high school geometry teacher would say that's impossible.
I love this because the math here is just an absolute stroke of genius.
Yeah.
It really is. Cordic works entirely by using bit shifts, additions, and table lookups. That's it.
But wait, how do bit shifts replace multiplication?
Okay, to understand this, you have to think about how binary numbers work. In our normal base 10 math, if you want to multiply something by 10, you just shift the decimal point one spot to the right, right?
Right, 10 becomes 100.
Exactly. Well, in a computer's binary system, multiplying or dividing by 2 is just a bit shift. You just move the ones and zeros left or right.
Oh, I see.
It doesn't require a dedicated, expensive multiplication circuit. It is practically free math on a hardware level.
So Cordic takes a giant rotation and breaks it down into a sequence of these smaller, predefined steps.
That is the trick. It restricts its micro-rotations to very specific angles. It uses a table that stores a series of pre-computed arctangent angles.
Okay, bear with me here.
The mathematical formula is the arctangent of 2 to the power of -i.
Hmm.
And because it only rotates by angles where the tangent is a power of 2, the math just requires those free bit shifts we talked about.
So it never has to do arbitrary multiplication.
Exactly. For each step, the algorithm looks at the remaining angle it needs to cover. It decides on a direction, which the text denotes as a variable die, either -1 or +1, and then it simply adds or subtracts the next predefined angle from the lookup table.
It's like navigating a maze in the dark, but you are only allowed to take steps that are exactly half the size of your previous step.
Yes.
You can't change the size of your stride. You can only choose whether to step left or right. And eventually, by just adding and subtracting those predefined steps, you zero in on the exact location you wanted.
And there is one crucial hurdle the algorithm has to clear here. Because you are taking these jagged predefined steps instead of a smooth geometric curve, the vector you are rotating actually stretches out.
Oh, right, because it's not a true circle.
Exactly. It gets a little bit longer with each step. So to fix this distortion, Cordic applies a gain compensation fallacy.
Like a magic number to shrink the line back down to its proper length.
Precisely. It's a constant, approximately 0.60725. And depending on how the engineer builds the system, this compensation is either driven by another lookup table or it's simply hard-coded into the final addition step.
That's brilliant.
The elegance of it really cannot be overstated. You
Okay.
replace massive, power-hungry multiplication hardware with cheap memory and simple addition.
And for you listening, why should you care about this algorithm from the 1950s? Because it is literally still everywhere.
Absolutely everywhere.
Every single time you turn your smartphone sideways to watch a video and the screen smoothly rotates from portrait to landscape, this exact fundamental multiplier-free math is firing off in the hardware to redraw those pixels.
Cordic proves that tables can replace complex mathematics.
Yeah.
But the true power of table lookup is that it isn't limited to math. It can replace complex logic in completely different fields, like cybersecurity.
Right. Here's where it gets really interesting, because Cordic shows us how a table replaces a math equation. But what happens when the roadblock isn't a math equation, but an incredibly complex security lock?
Let's talk about AES encryption.
Yes, AES. When you log into your bank, your data is secured by the AES standard. And inside that encryption pipeline is a step called the S box, or substitution box.
Right. During the encryption process, you have to scramble the data to make it unreadable. Mathematically, the S box requires calculating a multiplicative inverse in a highly complex structure called a Galois field, specifically GF2 to the 8th.
Okay, you lost me a bit there.
Fair enough. To put it simply, it requires an incredibly convoluted, nonlinear type of division.
Got it.
And doing that division on the fly for every single byte of data in, say, a 4K Netflix stream, it would bring your processor to an absolute crawl. The device would literally melt from the heat of those calculations.
So they don't do the math.
They completely skip it. The subbyte scrambling step is implemented as a pure 256-byte table lookup. They mapped every possible input to a pre-scrambled output.
So it's just a direct translation.
Yes, it provides that nonlinear substitution instantly. In computer science, we call this O1, meaning no matter how big the overall data set is, it takes exactly one single operation to get the answer.
And there's a fun fact in the sources about how far AES takes this.
The T tables.
Yeah. They use these 4 separate 256-word tables called T tables, and they use them to combine the substitution step, a shift rows step, and a mixed column step, all into a single lookup round.
It's incredible.
They basically smashed 3 separate heavy encryption operations into one giant cheat sheet.
The optimization is just relentless, and we see that same cheat sheet mentality in string matching.
Like searching for text.
Exactly. This is what happens when you hit C tree all else F to search for a specific word in a massive document. The source highlights algorithms like Boyer-Moore to show how tables speed up search.
To visualize this for the listener, imagine you are searching for the word APLE in a million-word document. You line up the word APLE against the text and check the letters. If you check the 5th letter and it's a Z, well, Z isn't anywhere in the word APLE.
A naive algorithm would just shift over one letter and start checking again.
Which is super slow. But Boyer-Moore uses a bad character shift table. The table basically taps you on the shoulder and says, hey, Z isn't in your target word at all. Skip ahead 5 whole spaces.
You leap over text you mathematically know is wrong. The table allows you to skip up to M characters, where M is the length of the pattern you are looking for.
That's so smart.
And the sources also detail the Knuth-Morris-Pratt, or KMP algorithm. It uses a prefix function, pi, as a table, to guarantee the search engine never has to backtrack.
So it only moves forward, guaranteed Owen performance.
Exactly. And for massive scale, the Aho-Karasik algorithm uses tables to map GOTO, failure, and output links. This allows the system to search for thousands of different patterns simultaneously in a single pass.
Okay, so tables dominate math, security, and search software. But what about the physical architecture of the computer itself?
If we connect this to the bigger picture, the hardware itself is physically reliant on tables to function at modern speeds. Let's look at the TLB, the translation look-aside buffer.
Right.
Every time a program needs a piece of data, it asks for a virtual memory address. But the physical RAM chip needs the actual physical location of the data.
It's like having a friend's name, but you need their actual street address to send them a letter.
Good analogy. To find that street address, the computer normally had to navigate a massive registry called page tables. It is a multi-step scavenger hunt that is painfully slow.
We call that a page walk, right?
Yes, a page walk. But a TLB is a tiny, super fast table built right into the CPU core that stores recent address translations. It's like putting a sticky note on your monitor with the 5 addresses you mail things to the most.
So you don't have to look them up in the directory every time.
Exactly. If the translation is in the TLB, the CPU gets the address in a single clock cycle, avoiding the page walk entirely and making memory access 10 to 100 times faster.
The sources also dive into branch target buffers and branch history tables, BTVs, and BHTs.
Right, because processors absolutely hate waiting. When code is running, it constantly encounters branches, like an if-then statement. It is a fork in the road.
And the CPU doesn't want to wait to see which way the code goes.
No, it wants to start processing the next instructions before it even finishes calculating which fork to take. So it uses these tables, often equipped with 2-bit saturating counters, to literally predict the future.
That is why.
It analyzes past behavior to guess which way the code will branch, predicting it with 0 cycles of delay. Not to mention decode ROMs offering single-cycle instruction decodes. The physical hardware is just tables all the way down.
And if the physical silicon relies on tables to run, the software we use to design that silicon takes this obsession to an absolute extreme.
Oh.
Yes, our sources dive deep into EDA, electronic design automation. This is the incredibly complex software that engineers use to design the chips inside our phones, our cars, everything. From the very first steps of synthesizing logic to the final sign-off, EDA tools run on tables.
They have to.
Let's start with logic synthesis. What happens when you map logic to an FPGA?
Well, an FPGA uses hardware units called KLUTs, lookup tables, to act as the programmable logic gates.
Right.
To design this efficiently, tools like ADC or CutMap pre-calculate all the possible ways to group the logic together. These groupings are called K-feasible cuts.
Okay.
For example, if an engineer is using a K=4 input system, there are at most 65,536 possible Boolean functions to classify.
That's a lot of combinations to figure out on the fly.
Which is why they don't do it on the fly. Instead of dynamically enumerating the logic during the design process, the software stores all those functions in a priority cut table.
So rather than building custom logic gates from scratch every single time, the software just pulls a pre-packaged Lego block of logic off the shelf.
Exactly. It's an O1 instant selection process rather than a massive calculation. And this methodology is crucial for STA, static timing analysis.
Now, this is the part that blows my mind. Making sure a chip with 2 billion tiny switches fires every single electrical signal on the exact right nanosecond. It seems impossible to just look up in a table.
Right, because the mathematically pure way to verify that timing is to run a SPICE simulation, which simulates the complex analog physics of the circuits, the voltage, the resistance, the capacitance.
Which is incredibly heavy.
Running SPICE on millions of gates would take a lifetime. So EDA tools use the liberty.lib delay model. It calculates the delay of a signal using a simple lookup table based on just two variables.
Input transition time and output load capacitance, right?
You got it. The signal enters the gate, and the weight of the wire it has to push on the way out.
It's like looking at a mileage chart on a map. You find your starting city on the left, your destination on the top, trace your fingers to where they meet, and boom, there is the delay time.
That's exactly how it works. They plot it on a grid and interpolate the answer between the points. They also use slew tables to check signal degradation, power LUTs, and POCV or SOCV derating tables to account for manufacturing variations in the silicon itself.
But the most aggressive use of tables is in physical design, right? With a tool called LLVOT.
Yes, LFUT, fast lookup table-based wire length estimation.
Say that 5 times fast.
I'd rather not. But, when you are physically placing components on a chip, you have to estimate the length of the microscopic wires connecting them.
Right.
The perfect geometric way to route these wires is called a rectilinear Steiner minimal tree. But calculating that tree is mathematically devastating. It's NP hard. It is a variation of the traveling salesman problem. As you add more connection points, the number of possible routes explodes exponentially.
So how does FLOT cheat the system? Because they clearly don't calculate it every time.
The creators realized they could pre-compute the mathematically perfect routing tree for any connection that has 9 pins or fewer. They stored all of those optimal routing shapes in a massive lookup table.
Wow.
If a connection requires more than 9 pins, the software just recursively chops the problem into smaller chunks and applies the table to the pieces. It turns a geometric nightmare that could crash a computer into an instant O1 lookup.
The last major area of EEA the sources cover is formal verification, which uses binary decision diagrams, or BDDs.
BDDs are how engineers mathematically prove that a chip design has 0 bugs before it goes to the factory for tape-out.
Right, because you can't issue a software patch for physical silicon.
Exactly. But to keep these diagrams from growing so large, they consume all the RAM on the server because without intervention, they blow up exponentially into massive decision trees. They rely on a unique table.
Okay, what does that do?
This ensures every node of the diagram is canonical, meaning the system never creates a duplicate representation of a logic path.
It's like a library system that prevents you from keeping multiple copies of the exact same book. If someone asks for a book you already have, you just point them to the existing copy.
Perfect analogy. And coupled with a computed table that acts as a memoization cache for previously solved subproblems, these tables keep the verification process grounded in reality instead of exploding into infinity.
Which brings us to a really practical question. We've established how crucial these tables are to making everything in our digital world fast.
Yeah.
But how do developers actually make the tables? Because historically, reading the sources, it was a really messy process.
Oh, it was terrible.
An engineer would have to write a separate Python script, run it to calculate all the math, have it spit out a massive text file full of thousands of numbers, and then somehow glue that text file into their C++ code using CMake during the build process.
It was duct tape engineering. But now, modern programming languages are pulling this entirely into the compile phase. This is the context for a revolution in modern C++ case.
Let's talk about that.
Starting a little bit in C++ 11, but heavily expanded in 14, 17, and 20, developers gain the ability to use the context pre-keyword.
Right.
It essentially tells the compiler, hey, do all of this heavy math right now on my powerful workstation while you are building the program, and just embed the final answer directly into the code as a static table.
It's the difference between a student having to do complex math during an exam versus the teacher just printing the answer key directly onto the test paper at the factory.
Okay.
By the time the code is running on the actual bare metal device, the math is completely gone. There's literally 0 runtime cost.
There is no initialization overhead when the program starts. You don't have to rely on external Python scripts holding your build process together. And you get guaranteed compile time validation that the table is correct before the software even ships.
Which is huge.
It's an absolute game changer for embedded systems, like the tiny chips inside a smart thermostat or a pacemaker, where memory and battery power are incredibly limited.
And the sources provide a brilliant case study for this, spotlighting a GitHub repository by a developer named Dress Loris. The project is called Corticrotate APFX. It loops right back to the algorithm we started with.
It really is one of the most explicit and elegant context prototype implementations available. It's written in standard C++14, targeting Xilinx high-level synthesis, which is a tool for designing custom silicon.
Right.
And what is impressive is that it standardizes the table generation entirely inside the compiler. The developer can easily customize the precision, like bit-accurate fixed-point precision, via template word length, and they can adjust the number of iterative Cortex stages, anywhere from 2 to 7.
And the compiler handles the rest.
Exactly. The compiler just seamlessly generates the read-only memory containing all those control signals and arctangent angles indexed by input angle. It even has a runtime Monte Carlo generator built in.
But the sources point out that this level of clean, compiler-driven table generation is actually quite rare in the wild.
It is.
Why don't we see this everywhere?
Well, what's fascinating here is that the main barrier was the language itself. Prior to the C++23 standard, the standard math function for arctangent std.8nin was not natively designated as a context spur.
Wait, so the compiler literally wasn't allowed to do the arctangent math itself to build the table?
Exactly. It would throw an error. If an engineer wanted the compiler to build the table, they had to write their own custom approximation of arctangent from scratch, or pull in heavy external libraries like Athorchim just to do compile time math.
That sounds exhausting.
It was. Furthermore, the EDA industry traditionally targets hardware description languages like Verilog, not C++1. And frankly, as messy as those old Python build scripts are, most engineering teams consider them good enough.
The classic engineering trap.
Exactly. The audience that is deeply passionate about perfectly clean, zero-script, high-level synthesis is a relatively niche group. But Draz Loris took the time to bridge that gap beautifully.
So what does this all mean? We've covered a massive amount of technical ground today, from the 1950s to modern compiler standards. Let's distill the key takeaways for you.
Okay.
Number 1, table lookup is essentially the original cache. You compute a painful problem once and you look up the answer forever. Number 2, the Cortic algorithm epitomizes this, replacing massive, expensive multiplication circuits with simple shifts, adds, and an arctangent cheat sheet.
Right.
Number 3, the EDA industry, the software that literally designs our physical hardware, fundamentally runs on tables to bypass mathematically devastating bottlenecks, like simulating analog physics or routing millions of wires.
They absolutely depend on it.
And finally, modern language features like C++ context spur are turning table generation into an art form, moving the computational burden entirely off the tiny device in your pocket and onto the massive compiler back in the lab. The overarching lesson: the absolute best algorithm in the world is the one you never actually have to run.
And, as memory density continues to skyrocket year after year and compile time computing becomes virtually limitless, it really raises a fascinating question.
Oh.
Are we moving toward a future where runtime calculation completely disappears?
Wow.
I mean, think about it. If memory becomes infinite and cheap enough, will the software of tomorrow just be one massive continuous lookup table where every possible outcome is already mapped?
That is a wild thought to leave you with. If every decision is pre-calculated, is the computer really thinking or is it just reading? Thank you so much for joining us on this deep dive. Keep questioning how your systems actually work beneath the surface. And as always, happy optimizing.